Okay, good afternoon. So I'll be presenting two videos, which are about, the first one is the fundamentals of frequency modulation. So this video is actually created by Schwarz. Okay, a very good video to understand, the basics of frequency modulation. And the second video will be about the radio frequency technologies and its applications. So in this video, also the overview of the RF test or radio frequency test and measurement is discussed. Okay, so please watch and answer the corresponding activity related to these videos.
Frequency modulation, including related concepts such as frequency deviation, deviation ratio, and the difference between narrowband and wideband FM. Modulation is the process of varying a transmitted carrier in order to convey information. There are three things we can change about a sine wave: its frequency, its phase, and its amplitude. In frequency modulation, or FM, we convey information by changing the frequency of the carrier. The two most common applications of frequency modulation are commercial FM broadcasting, or FM radio, and local two-way communications. Because frequency modulated signals require relatively wide bandwidths, FM is normally only used at VHF and higher frequencies, that is, at frequencies above 30 MHz. FM is almost exclusively used to transmit audio, either speech or music, and as we'll see, one of the major advantages of FM is that it can provide both high quality and high immunity to interference, fading, etc. FM signals are created using an FM modulator, the inputs to which are an unmodulated RF carrier and a low-frequency modulating signal. The result is a modulated RF carrier whose frequency continuously increases and decreases based on the amplitude of the modulating signal. Frequency modulation offers quite a few advantages over other forms of analog signal modulation. Because FM transmits information as changes in frequency, it's relatively immune to changes in signal amplitude, such as those caused by fluctuations in the received signal level, noise, interference, etc. This makes FM a good choice for mobile or portable communications, where the RF and propagation environment may be rapidly changing. And since amplitude is not used to convey information, FM can also use so-called non-linear amplifiers, whose efficiency provides an advantage in terms of power consumption and thus longer battery life. Again, this is important for portable operation. However, FM does have a relatively poor spectral efficiency compared to other analog modulation schemes, like conventional AM or single sideband, in that it requires much wider bandwidths. The width of an FM signal is a function of its frequency deviation. Remember that in FM, the carrier frequency, F sub C, changes based on the modulating signal. In other words, the carrier moves up and down in frequency as the modulating signal changes. A very important concept in FM is deviation, which is the current distance, in hertz, of the carrier from the nominal center frequency of the signal. This deviation can be either positive or negative. For example, a deviation of 15 kHz means that the carrier is currently 15 kHz above the nominal center frequency. In many cases, when people talk about the deviation of an FM signal, what they really mean is the maximum deviation of the signal, that is, the maximum distance away from the center. This value is a function of the design and configuration of the transmitter and is chosen to meet the requirements of the application and the amount of available spectrum. Deviation ratio is the ratio of the maximum frequency deviation to the maximum modulating frequency. The deviation ratio will be different depending on the application. For example, music has a relatively high maximum modulating frequency, and this in turn requires a relatively high frequency deviation if we want good audio quality. On the other hand, normal human speech has a lower maximum modulating frequency, so we can use a lower deviation and still have intelligible signals. Deviation ratio is often used to group FM signals into two general categories: wideband FM, which has a deviation ratio of greater than 1, and narrowband FM, which has a deviation ratio of less than 1. Let's look at the differences between these two different categories of FM. Wideband FM generally has a relatively high maximum deviation, usually 75 kHz, and a high deviation ratio, typically about 5. As mentioned earlier, using a larger value for deviation provides better audio quality, especially in the case of music, but this also increases the resulting bandwidth of the FM signal. As you might expect, wideband FM is most commonly used by commercial broadcasters. In the United States, these signals can be found from 87.9 to 107.9 megahertz, with stations spaced 200 kilohertz apart. Narrowband FM has a much lower maximum deviation compared to wideband FM, usually only 3 to 5 kilohertz. By definition, the deviation ratio of narrowband FM signals is always less than 1, and in practice they tend to be somewhere around 0.5, although this can vary widely between radios and applications. This lower deviation ratio means lower audio quality, but also a narrower signal bandwidth, and thus narrowband FM is normally used for two-way voice communications. Typical channel widths are usually 12.5 or 25 kilohertz, although this too can vary depending on the application. We can approximate the bandwidth of an FM signal using something called Carson's rule. This rule is named after John Renshaw Carson, who first formulated it in 1922. Carson's rule defines the bandwidth of an FM signal as the region that contains 98% of the total signal power, and this can be computed by adding the maximum frequency deviation to the maximum modulating frequency and then multiplying this sum by 2. For example, a commercial FM broadcast station with a maximum frequency deviation of 75 kilohertz and a maximum modulating frequency of 15 kilohertz would have a bandwidth of approximately 180 kilohertz. FM broadcast stations are spaced 200 kilohertz apart to provide an additional guard band to prevent interference between adjacent frequencies. So in summary, frequency modulation carries information by changing the frequency of the carrier. The greatest advantages of FM are that it provides high-quality audio and is relatively immune to amplitude variations caused by things like fading, noise, and interference. It does, however, require significantly wider bandwidths than other analog modulation types. An important concept in FM is deviation, which is the distance that the carrier moves from the nominal center frequency. Deviation ratio is the maximum deviation divided by the maximum modulating frequency, and FM is often divided into narrowband and wideband based on this deviation ratio. Finally, we can use Carson's rule to approximate the bandwidth of an FM signal. This concludes our presentation, Understanding Frequency Modulation. Thanks for watching. Hello, and welcome to this presentation. What is RF? In this presentation, we'll provide a general, non-technical introduction to RF, or radio frequency technologies, the different ways that RF is used, and a brief overview of the most common instruments found in radio frequency test and measurement. To understand RF, we first need to talk about the two different types of electricity. The first of these is direct current, or DC. A common household battery is an example of a source of DC power. In DC, the amount of voltage or current produced typically remains constant over time. The second type is alternating current, or AC. The electrical outlets in your home provide a voltage or current that rises and falls over time. The rate at which this current rises and falls is called the frequency. Frequency describes how many times per second the current goes through one complete cycle of rising and falling before returning to its original level. The number of cycles per second is measured in units of hertz. For example, if this is 1 second and the current goes through 4 complete cycles in 1 second, then the frequency is 4 hertz. In the United States, the frequency of AC power in wall outlets is normally 60 hertz, meaning the current completes 60 cycles in 1 second. Any alternating current that moves through a conductor, such as a wire or an antenna, also generates an electromagnetic field that travels outwards into space. At very low frequencies, such as the 60 Hz AC we just mentioned, this electromagnetic field is not particularly strong and will not travel very far. Radio frequency, or RF, refers to energy whose frequency is high enough to efficiently radiate into space. There's no strict definition of what makes something radio frequency, but most engineers would consider RF to be electromagnetic energy in the range of about 20 kilohertz to about 300 gigahertz. That is 20,000 to 300 billion cycles per second. Although the most important aspect of RF is the fact that it can propagate through space, RF can also be carried by cables or other conductors. A common example of this is cable television signals sent within coaxial or coax cables. RF is also conducted between components in electronic devices, such as within a cell phone or a GPS receiver. And most radio frequency test and measurement applications have traditionally used conducted RF. There are three general uses for RF. The first, and by far the most common and most important, is transferring information. Radio and television broadcasts were among the first uses of RF for transferring information in the form of sounds and images. And we've already mentioned that cable television also uses radio frequency signals. The properties of RF enable modern data transmission technologies, such as Wi Fi, cellular voice and data, Bluetooth, etc. And obviously, the ability to transmit information through space is extremely important for satellite applications, including GPS. Another area of use for RF is sensing or detecting objects. Here, RF is transmitted, and the characteristics of the received RF can provide us with information about the objects that it encounters. Radar is a very well known example of this. The body scanners found in airports also use RF to detect objects. And RF can even be used to measure the properties of materials. The third main category of RF applications involves heating objects. This includes both microwave ovens, as well as industrial and medical applications. Since almost everyone is familiar with using RF to heat objects, we'll start there. Microwave ovens use something called a magnetron to create RF at a frequency of about 2.5 gigahertz. This is, incidentally, in the same frequency range commonly used by Wi Fi and Bluetooth. This RF then penetrates foods or liquids and causes the molecules, more specifically water, to vibrate, and this vibration creates heat. One common warning when it comes to using RF to heat food in a microwave oven is to avoid having metal objects in the oven. This is because the metal can turn the radiated RF produced by the magnetron back into conducted RF, and the resulting currents in the metal can cause sparks, fires, etc. In addition to warming up leftovers, RF is also used for heating in industrial applications, such as pasteurizing milk, and is now also found in some medical applications, ranging from destroying cancerous cells to various cosmetic treatments. At this point, it might be worth pausing to talk about RF safety. Some kinds of radiated energy, such as X rays, gamma rays, and UV or ultraviolet rays, are so called ionizing radiation. Ionizing means that this energy can break apart atoms or molecules, including DNA, and can be a direct cause of certain forms of cancer and other health issues. RF, on the other hand, is non ionizing radiation. This means that RF doesn't break apart atoms or molecules. That doesn't mean that RF is completely harmless. As we've just discussed, RF can create heating, and at very high levels, this can lead to tissue damage. However, there's no firm or conclusive evidence that RF poses a significant danger to living creatures at common power levels or under normal circumstances. High power transmitters do, however, require caution, and it's always best to follow the regulatory and/or industry guidelines when it comes to RF exposure. Standing in front of an operational high power radar, for example, is definitely not recommended. Radar is, however, an excellent example of how objects can be sensed using RF. We transmit RF and examine what comes back. Most people are familiar with various radar applications, such as detecting planes or ships, or measuring the speed of a vehicle or a baseball. One of the more common examples of using RF for sensing are the body scanners that have largely replaced metal detectors in airports. Some types of motion sensors and alarm or other systems also use RF. A less well-known use of RF for sensing is something called material measurements. RF allows us to non-destructively determine certain properties of materials, such as checking tissue for the presence of breast cancer, or trees for the presence of rot, termites, etc. But as mentioned earlier, the most common use of RF in the modern world is to transfer information without wires or over the air. In order to transfer information using RF, we have to change one or more properties of the generated electromagnetic field, and this process is called modulation. The simplest way of changing something about our radiated field is just turning it on and off, and this is essentially how Morse code works. We turn the RF on for a short period of time when we want to send a dot, and we turn it on for a longer period of time when we want to send a dash. The next step up from this on-off approach is amplitude modulation, or AM, where we change the strength of the RF to convey information. In frequency modulation, or FM, we change the frequency of the radiated signal, depending on the information we want to send. Both AM and FM are primarily used for analog modulation, such as in radio broadcasts. On the other hand, if we want to send digital information, we typically use more complicated modulation schemes, often changing both the amplitude and the phase or frequency shift of the RF at the same time. The definition of RF covers a very wide range of frequencies, but the specific frequency used is largely based on the application. Generally speaking, two things happen as we lower the frequency. First, the radiated fields propagate or travel longer distances. Second, lower frequency signals also tend to penetrate or pass through objects more easily. The opposite is true for higher frequencies. For example, broadcast AM radio uses frequencies in the hundreds of kilohertz, and broadcast FM radio uses frequencies around 100 megahertz, because we want these relatively low frequency signals to travel many kilometers and be receivable inside of buildings, houses, etc. On the other hand, Wi-Fi is at either 2.4 or 5 gigahertz, that is, at frequencies that are 25 to 50 times higher than those used for AM or FM broadcasts. One of the reasons for using these much higher frequencies is that we don't want Wi-Fi signals traveling too far. Your access point is essentially noise or interference to everyone else's access point, so it's better for everyone if our Wi-Fi signals don't extend much beyond our own homes or businesses. In most parts of the world, the right to use a given frequency or range of frequencies is set by a government or regulatory agency. In the United States, this is the Federal Communications Commission, or FCC. Acquiring the license to use certain frequencies often requires a fee, and the cost can be quite substantial. Cellular network operators, for example, pay billions of dollars for the exclusive right to use certain frequencies. Because human beings can't normally sense radio frequency energy, RF test and measurement equipment is necessary for the design, test, manufacture, and debug of radio frequency devices. Every device that uses RF, from TVs and radios to Wi-Fi, cell phones, GPS, radar, etc., was created using RF test and measurement instruments. There are four basic categories of RF instruments, namely spectrum analyzers, signal generators, network analyzers, and power sensors, and we'll spend a few moments explaining what each of these instruments does. The first instrument we'll talk about is something called a spectrum analyzer, so it might be a good idea to spend a moment explaining what we mean by spectrum. The word spectrum generally refers to a range of frequencies. As human beings, we can perceive two different types of spectrum. What we call color is simply how our eyes and brain interpret different frequencies of light. And our ears can also detect and distinguish sounds, that is, vibrations of the air, at different frequencies. But as we mentioned earlier, the radio frequency spectrum is not humanly perceivable. We normally can't sense RF at all, and we certainly can't distinguish how much energy is present at different frequencies. Instead, we use a special instrument called a spectrum analyzer to obtain this information. When we use this instrument to analyze spectrum, we typically want to detect and measure what kinds of signals are present and at which frequencies, their powers, any modulation, etc. In most cases, spectrum analyzers are used in a laboratory environment, but there are also portable spectrum analyzers that are specifically designed to be used outside or in the field. The most basic function of a spectrum analyzer is displaying power versus frequency. This is a fancy way of saying that we want to know where RF is present and how much RF is present. In many cases, power is measured relative to other powers and is therefore expressed in dB or decibels. In addition to the basic power versus frequency display, many spectrum analyzers can also demodulate different types of signals. These can be very basic analog signals like those used in FM radio, or it can be quite complex digital signals like those used in LTE, 5G, Wi-Fi, etc. Demodulation means extracting the information in a signal, but can also be used to tell us things like how much error or inaccuracy there is in a modulated or information-carrying signal. When a spectrum analyzer is used in this way, it's often referred to as a signal analyzer. In the real world, radio frequency signals come from various devices, such as your cell phone, a car remote, a GPS satellite, etc. An instrument called a signal generator can be used to create the different types of RF signals needed to design and test RF devices. These signals can be simple, unmodulated signals, or can be complex modulated signals like those used in most wireless communication systems. A signal generator allows the user to control all of the parameters of the signals that it generates, including power, frequency, and modulation. Most signal generators are used for testing devices during design and debug, and therefore they're primarily found in labs. A very common combination of test and measurement instruments is a spectrum analyzer and a signal generator. For example, imagine that our DUT, or device under test, is an amplifier. We can use a signal generator to generate a signal that is sent into the DUT. The amplified signal can then be measured and analyzed using a spectrum analyzer. In some cases, we can think of our device under test as something called a network. In the RF world, a network is a device that has one or more ports, each of which can pass, reflect, and/or absorb radio frequency energy. These are usually components in a system, and the typical cell phone has many components that can be described as a network. It's important that these components work properly to ensure the performance of the entire system, and therefore we need an accurate, reliable, and repeatable way to measure them. Networks are tested by injecting RF into one of the ports and simultaneously measuring how much RF is reflected back from that port and how much RF comes out of the other ports. We also might be concerned with how much delay is introduced by the network, or how the network changes other characteristics of the injected signal. In order to analyze networks, we use a network analyzer. A network analyzer both generates and measures RF energy simultaneously, and thus is similar to the combination of a signal generator and spectrum analyzer. In most cases, network analyzers are very high precision instruments that are able to measure small variations or changes in signals, and sophisticated calibration routines are used to further minimize or remove error. Since they're most often used to measure components, network analyzers are most commonly found in labs, although portable network analyzers can be used in the field for testing things such as cables and antennas. You may also hear network analyzers referred to as vector network analyzers, or VNAs. Sometimes our goal in RF test and measurement is just to measure RF power. Although spectrum analyzers and VNAs can measure RF power, small, relatively inexpensive instruments called power sensors are often used when all we need is a simple measure of received power. The basic functionality of a power sensor, therefore, is simply reporting a number, such as 10.92 dBm. Power sensors may not be as sophisticated as the other instruments we mentioned, but they're very widely used in the RF world and can be easily found in most RF labs. One of the biggest advantages of RF is that it allows communications without cables or wires. That said, most RF testing uses cables to move signals between the instrument and the DUT, or device under test. By using conducted RF, we can more precisely control things like the power levels received by the DUT. However, some of the more recent technologies, such as 5G, require so-called over-the-air, or OTA testing, where signals are radiated into and/or out of the device under test. This is mostly due to the higher frequencies used in these technologies and the lack of an RF connector on the DUT. In this case, testing usually requires special shielded boxes or chambers in order to keep other RF signals from getting in and prevents our test signals from radiating out. In addition to the four categories we mentioned earlier, there are many other types of RF test and measurement instruments. Communications testers are something of a combination of a signal generator and a spectrum or signal analyzer, and they're designed to test wireless communications devices, such as cell phones, Wi-Fi and Bluetooth devices, etc. These testers can emulate a wireless device, a wireless access point, or a cellular base station, and allow both voice and data testing. In EMC, or electromagnetic compatibility testing, we're interested in two things. First, whether electrically powered devices are unintentionally radiating RF that could interfere with other devices. For example, whether a washing machine interferes with our cell phone reception. Conversely, we might also want to check if devices are adversely affected by RF. In this case, whether our cellular devices or base stations cause washing machines to malfunction. Closely related to EMC testing are amplifiers, which boost RF signal power and therefore can be used to create the high power RF signals that are needed in some EMC tests. And finally, oscilloscopes are another category of RF test and measurement instruments. Scopes are most often used for non-RF electrical testing, but can also be used in numerous RF applications as well. Let's end with a brief summary of what we've covered. Alternating electrical currents produce electromagnetic fields. When the frequency of these fields is high enough to radiate efficiently through space, we refer to this as radio frequency, or RF. RF is used in three main areas. First and foremost, RF can be used to transfer information over long distances without wires or cables, such as TV and radio broadcasts, satellite communications, cell phones, and Wi Fi. RF is also commonly used to sense and detect objects. Examples of this are things like radar and airport body scanners. And almost everyone has firsthand experience using RF to heat objects in a microwave oven. Because human beings can't directly sense or measure RF under normal circumstances, RF test and measurement instruments are needed in the design, test, manufacture, and debugging of radio frequency devices. This concludes our presentation, What is RF? If you'd like to learn more about RF and radio frequency test and measurement, please follow the links in the video description. Thanks for watching.
Again, so thank you for being here, and I hope you learned something in the video that you have watched. So again, you're going to make a comprehensive report about those two videos that you have watched. So understanding FM and what is RF. So if you click this once, you'll be redirected to the video you have watched. So courtesy of,
Frequency modulation, including related concepts.
okay, yan, si Paul, yung nag-narrate itong video. Okay, and the other one is RF. So, ayan. So, minimum of 500 words. So, don't limit to 500 words lang. So, of course, comprehensive siya. So, you need to, write everything that you have, learned in the video. Okay? Any questions or clarification? Is it okay, guys? Is it too much? Not really. Okay. Okay lang? Pagaling wala sa